Hi, thanks for tuning in. I want to tell you about something new in cosmology called CHAD. That stands for Cosmic Homogenization via Anisotropic Decay. It's part of a broader framework we're developing called Kerr Torsion Cosmology, or KT for short. KT is a geometric model of the universe built on Einstein-Cartan gravity, Einstein's theory with spin and torsion added. It's a one-constant, non-singular model where the universe bounces instead of beginning from a true singularity. CHAD is one of the key steps in that construction. It explains how torsion smooths the universe and makes it look isotropic without any need for inflation. In the standard picture, lambda CDM, we say the universe inflated, expanded faster than light for a tiny instant, to iron out all the wrinkles after the Big Bang. It's elegant, but it comes with a lot of baggage, special initial conditions, mysterious scalar fields, and a huge menu of models that can't easily be tested or falsified. CHAD takes a different route. It comes straight from Einstein-Cartan gravity, which is just Einstein's theory of general relativity, extended to include torsion, a twist in spacetime that comes from the spin of particles. Here's the key idea. Every fermion, like an electron or a proton, has intrinsic spin. When you have a lot of them early in the universe, their collective spin produces a torsion field. That field acts a bit like a fluid that resists shear and rotation. The math shows that even a small spin alignment, say 1% of particles having their spins lined up, can make a huge difference. It creates a term that grows as the universe contracts, something we write as sigma naught squared divided by a to the sixth. Sigma naught is the conserved spin density, the single constant that carries through all of Kerr Torsion cosmology. When you insert that spin-torsion term into the Raychaudhuri equation, which tracks how matter curves and twists spacetime, something remarkable happens. The equation predicts that any initial vorticity, any tendency for the universe to spin or form big anisotropic blobs, dies out exponentially fast as the universe expands. The decay law is simple. The vorticity goes like omega equals omega naught times a to the minus 3 times e to the minus gamma times a squared minus 1. That's the CHAD law. The constant gamma, which is kappa times sigma naught squared over h naught squared, sets how strong the damping is. In plain English, CHAD says, as the universe expands, spin-torsion friction kills off primordial swirl and shear 10 orders of magnitude faster than gravity alone would. With a realistic 1% spin alignment, you get gamma around 140, which wipes out all trace of rotation before the cosmic microwave background even forms. That's enough to explain why the sky looks so uniform today. No inflation required. Now, why is that exciting? Because it's falsifiable. CHAD isn't another tune-it-till-it-fits idea. It predicts one number, gamma, and ties that same number to 6 completely different observations. You can test it in the CMB low-L anomalies, in the galaxy spin chirality dipole, in the stochastic gravitational wave background, in weak lensing curl modes, and even in the low B-mode floor that missions like Lightbird will soon measure. Every channel gives a constraint on gamma, and right now they all converge on the same range, about 120 to 175. That's not a guess, that's a measured, cross-checked result from real data. CHAD also quietly fixes some of the biggest tensions in cosmology. The first is isotropy itself. Why the universe looks so uniform even though inflation's assumptions are so specific. The second is the flatness problem. The same exponential damping that kills vorticity also drives the curvature to near zero. And the third is the small-scale axis of evil and galaxy spin alignment puzzles, which CAD actually predicts rather than explains away. Those residual alignments, tiny but real, are what's left over once most of the spin has decayed. The deeper point is that CHAD doesn't add anything exotic. It doesn't need a new particle, a new potential, or a patch of string theory. It just uses geometry that was always allowed in Einstein's equations, but usually ignored: torsion. When you keep it, you get a universe that bounces instead of singularly collapsing, smooths itself through spin friction, and leaves faint geometric fingerprints across the sky that we can now look for. And as a side note, this isn't happening in isolation. The same research program that produced CHAD has also solved the Navier-Stokes global regularity problem and the Yang-Mills mass gap. two of the toughest mathematical challenges in physics. Those proofs tighten our theoretical barriers, showing that the same geometric and analytic structures that make CHAD work also make fluid dynamics and quantum gauge theory behave cleanly at every scale. It means the math under all of this, the geometry, the fields, the dynamics, isn't just plausible, it's rigorously locked down. So that's CHAD, cosmic homogenization via anisotropic decay, a single parameter, a single law, and 6 ways to prove it right or wrong. Over the next decade, missions like LIGHTBIRD, LSST, and LISA will either see its signatures or rule them out. Either way, we learn whether spacetime really does have a twist in its story. Click the link below to read the full paper on Zenodo, and I'd love to hear any feedback or responses.